This screencast is on the use of the Nernst equation to determine what a cell potential, how a cell potential will change from standard. So qualitatively, we can predict the direction of the change of that cell potential from Le Chatelier's principle. Some of the activities we did earlier in the week, we were able to see that if a reaction were changed in such a way that it favored the forward reaction, we would see the cell voltage go up. So we have our standard cell voltage here with zinc and copper. And we know that it is standard because, one, we have this little indication of that little zero there. And we know that standard is at 25 degree, 1 atmosphere, and 1 molar solutions. So as we change those concentrations of our ions, our E cell is also going to change. So if we look at this one here that is in red, we'll see that with these changes, we have copper increasing from 1 molar to 1.5. Add shifts away, and so it is going to favor that forward reaction. We're kind of doing this double time because we've also decreased the concentration of zinc, remove shifts towards. So again, both of those changes favor the forward reaction according to Le Chatelier, and we see that our cell voltage increases. On the other end of that, if we make changes to our cell that cause it to shift in the reverse reaction, as in this one right here, we would see that the cell voltage decreases when compared to the standard cell potential. And while we can make these qualitative changes or decisions about or predictions about that cell voltage, the AP exam is going to want something a little more concrete when they ask us what's going to happen to the cell potential compared to the standard. So we're going to talk about that. One thing that we're going to need for the Nernst equation, which is how we're going to quantitatively talk about the cell potential, is we need to talk about this concept of the reaction quotient, which is Q. Now, this should seem at least a little bit familiar because the way we find Q is the exact same way we find K when we're looking at equilibrium expressions. And Q is related to K, and they're found the exact same way, except K is at equilibrium and Q is in conditions that are not at equilibrium. So when we are finding this reaction quotient, if I have a reaction here with my capital letters representing my substances and the lowercase letters representing my coefficients, what Q would look like is it's always the concentration of the products over reactants raised to their coefficient power every single time. All right. Now, this plays an important role in the Nernst equation. The Nernst equation is not given to you on the reference materials, and you will not have to do exact calculations using the Nernst equation. But you can use the Nernst equation and what it tells us to give kind of a backbone to your predictions that you came up with Le Chatelier's principle. So here I have that zinc copper battery that we were dealing with before and that we actually made. And so we're going to go ahead and we're going to write our Q for this because here is our Nernst equation. All right. So we're going to need Q. I'll just go ahead and get it done since we're practicing that. Q for this one are my products over my reactants raised to the coefficient power. This is done the exact same way that we would do equilibrium, and so we leave out pure solids and pure liquids. And so what this is going to look like, my product is zinc ion concentration over my copper ion concentration. And if there were coefficients in front of here, we would have them to that power. So this is Q for this particular reaction. I've also calculated my standard cell potential from my cathode minus anode using those standard reduction tables. And that's stuff we've practiced before. And that's how I got that 1.10 volts there. All right, so now let's look at the Nernst equation. So with the Nernst equation, what we have is the relationship between our cell potential and the cell potential or the standard cell potential. All right, so how is our cell potential going to change if we move away from those standard conditions? All right, so for this one, we're going to look at our cell potential. And we already have our standard cell potential already figured out. So that's going to be 1.10 volts. All right, then it's going to be minus. So here's how it's going to change. And it involves this quantity right here. Now, R has to be the 8.314 because that is the one that has joules in it. And joules are related to volts with coulombs. So we have to get all of those involved. Temperature is the temperature that's going to be in Kelvin. N is the moles of electrons, so how many electrons are moving in a particular substance. And F is Faraday's constant, that 96,500 coulombs per mole of electrons. So one of the things that we want to look at, because we don't actually have to do calculations with this, and all of that is times the natural log of Q, is this for a particular reaction is all going to kind of be the same. It's going to be a number, just a number. Here's where it's going to change according to concentration. So it's the natural log of Q. And here I have Q expression written down here. Now, when you're dealing with natural logs, we got to know a few little things about that. So the natural log of 1 is equal to 0. So if Q equals 1, natural log of 1 equals 0. So if Q is equal to 1, then it is 0. Well, if the natural log of Q is 0, that makes this whole term right here equal to 0. So our cell potential, our E, is equal to our standard cell potential. And that's how that works out. So if Q is equal to 1, your cell potential is equal to your standard cell potential, according to the Nernst equation. Now, other things about natural logs. If you have natural log of something that is less than 1, like natural log of 0.1, you're going to find that that ends up giving you a negative number. So that means, let me go up here and talk about this again. That means that this quantity right here is a negative number. So a negative times this value, which is a number, and we're going to be subtracting. So it's going to make this whole term negative, which means we're going to in turn add whatever the number is to our cell potential. So that's going to make our cell potential greater than our standard cell potential because we're going to be adding more to it. So if Q is less than, let's try that again. If Q is less than 1, then our cell potential will increase. Now, let's make sure that jives with Le Chatelier's principle. If we look back at our Q expression, to make Q less than 1 means I need to increase my copper ion concentration. If I increase my copper ion concentration, add shifts away, it's going to favor the forward reaction and the cell potential will increase, according to Le Chatelier. So it does jive with what we've been talking about with our Le Chatelier's principle. Let's look at another one. If go back to natural logs. So if I have a natural log of a positive number that is greater than 1, so 1.1, what you end up with is a positive value for Q. So then it will end up being positive, which is going to end up, this whole term will be positive, meaning we're going to subtract our standard cell potential by a number. subtract a number from our standard cell potential. So our cell potential will decrease. So if Q is greater than 1, then our cell potential decreases according to the Nernst equation. And that's how you would write it there. Again, let's make sure that that jives with what we were talking about with Le Chatelier's principle. All right. So in order to get Q, a number greater than 1, I could increase the amount of zinc ions. So if I increase the amount of zinc ions, add shifts away, so the reverse reaction would be favored, and we know that our cell potential will decrease from that standard. So that is how you are going to use the Nernst equation. We never actually plugged in any of the numbers and actually calculated, but it was reasoning through with this understanding of what Q is. And we'll continue to work with that. We're going to see more of Q and this change from the standard to non-standard conditions with our cell potentials.